All right, the next section is the piezoelectric versus capacitive accelerometer data. Now, this is important because we need to talk about the hardware that makes Actigraphy possible. The traditional classical version is the piezoelectric accelerometer. Now, these devices use a simple principle. You have a piezoelectric crystal, which is attached to the seismic mass. And then whenever there's a mechanical stress along the sensitive axis, the KISS crystal or the piezoelectric element generates an electric charge. And when acceleration occurs, these crystals deform more materially, producing a measurable voltage that corresponds to the movement. And that's what these devices are measuring to assess acceleration of movement. So small movements generate small voltage signals, while large movements generates large voltage signals. About 2010 or so, we saw a significant shift towards capacitive MEMS accelerometers. Now, these work quite differently. They use a movable plate that's usually attached to springs with components like shown here that are positioned between fixed outer plates. This creates a capacitive relationship, or in this case, multiple capacitive relationships. And as acceleration occurs, the distance between these plates changes, changing the capacitance. And the change in capacitance is then used to calculate the actual acceleration. Now, piezoelectric accelerometers have some advantages, and this is a table that I pulled from analog.com. It generally has lower noise levels compared to the capacitive MEMS. It also has a larger spectral range and is particularly good at larger and higher frequency ranges. However, the MEMS accelerometers are cheaper, have a longer battery life, and have electronic capabilities which make it easily integrated into electrical circuitry. One of this is the possibility to do a self-test so that it could sort of see if the component is self-working, whereas that's not an option for the piezoelectric accelerometer. They also have some integrated electronics in these MEMS accelerometers so that you can have digital outputs and interfaces which allow direct communication with microcontrollers or other digital systems. And so as a result, MEMS accelerometers have really sort of entered into the hardware space simply because it's better suited for low power portable applications where space is limited. And so this is why you can appreciate that MEMS accelerometers has really taken over into the wearable space. And this is certainly true in the sleep actigraphy space. So the traditional actigraphy devices, such as Philips and AMI motion loggers, both use piezoelectric accelerometers. But the newer contemporary devices, such as Gene Active, Actigraph Leap, and Garmin VS4 all have the capacitive MEMS accelerometers instead. And this is just proof of that to show here. This is sort of the brochure that comes with ActiWatch, which is, as you know, no longer available. It has a solid state piezoelectric component, whereas the contemporary devices such as Gene Active has a MEMS device. And this is also true for the newer Actigraph, which also has the MEMS accelerometer hardware in it. So why should this matter for sleep activity? Well, there are two important differences in the way acceleration data is generated and formatted. First is the piezoelectric material only responds to changing stress. So they cannot generate a constant signal response to steady forces like gravity. So as a result of that, there's no DC response, while the MEMS accelerometer does. So in other words, you can assess gravity in MEMS accelerometer, but not in the piezoelectric accelerometer. The other difference is that because the capacitive sensors are smaller, you're able to compact or put 3 different axes into the same device. So capacitive MEMS have 3 axes, whereas the piezoelectric has only 1. And you could see, obviously, the differences in there. And you could also see the DC, or the direct component here, which denotes gravity. And you could see, when the person sort of rotating their wrist, it's showing sort of changes in the values of the low frequencies here. And this is a crucial point that's overlooked because all our common sleep actigraphy algorithms, such as the Capacitive and SAT-A, others were originally developed using data from piezoelectric accelerometers, specifically the AMI motion logger. And so this is the actual publication of the Capacitive in 1992, and you could see that it used a motion logger again, and the SAT-A method back in 1994 also used the AMI motion logger. I think when it's really important is that this is just not a historical footnote, because when we use modern capacitive MEMS accelerometers where the 3-axis data, we can't simply plug this data directly into these traditional algorithms. The signal characteristics are fundamentally different, requiring additional processing steps to make our modern data compatible with these classic algorithms. And so this is where this needs to be reevaluated, this first step of how the acceleration raw data is transformed into activity count. So here are the steps that needs to be taken in order to do that. Now, so this is an example of raw data. This is demarcated here as UFX, UFY, UFZ. And what we need to do is to do two things. First, to eliminate the gravity factor, and you do this by applying a bandpass filter or moving average. And you can see that that's sort of like the wandering baseline here. The other thing that we need to do is combine these 3 accelerations into one. And we do this by creating an amplitude or a vector magnitude. So let's just say we take this raw filter and then we first apply a bandpass filter. And so we could do that here, which is transformed to F, X, Y, and Z. And so you can see this wandering baseline is eliminated, and you can see all these components. And then you could do step number 2, which is the vector magnitude. And you get what's here called FMpre, and you get this type of looking data. Now, let's just say you do the vector magnitude first, and you get UFM, and then afterwards, you apply the bandpass filtering. You get a completely different, or it looks very different than the FMpre. So this is why sort of in the options for the Garmin Enhanced Actigraphy, you have the option for FMpre and FMpost. These two provide very different results. And it's the order by which you are doing these filtering or this processing that matters. So whether you do the filtering first in FMpre or filtering afterwards in FMpost can really change your results. Now here you could kind of see here that the gravity vector magnitude is 1. And so there's another option. It's just to simply eliminate this 1, establish 0, and then to create an absolute value. And so there's another option here, which is called UFM. So the question is, which one should you use? Should you use FMpre or FMpost? And I wanted to go a little bit of the intricacy of this because it gives you an idea of this is not being really that straightforward here. So this is an individual. So I have to thank Dr. Huang, who is part of our team. He placed an ActiWatch on while also placing a MEMS accelerometer on the same wrist. And you could see here that, how this data sort of looks very similar to this. And what we do is that we can apply the FMpost and we get this result. Now, what if we do the same thing, but we do FMpre? So instead, what we do is apply a filter first and then apply the amplitude vector. And then you can see again that the results are different. First of all, the FMpre tends to all be positive because the act of this vector magnitude makes everything positive. The other thing is these small motions here that you see here are shown up here, but not shown up on the FMpost. Now, why is that? It's because the FMpost has almost a preferential bias towards the axis that is more oriented towards gravity. So you could see here that, the value for the z-axis is 800 and to 900. So it's almost like because the watch is positioned like this, it's almost like your wrist is positioned like that. And so what FMpost does is that it sort of biases these motions that you see in this z-axis because it is aligned with gravity and it shows up here, whereas the motions that you see in the ones that are in the other axis are not appearing here. And so that is an important differentiation between the two. And this is just another example, again, courtesy of Dr. Wang, also part of our data science team. He actually wore these devices while he was asleep with the lights on, with the video recording. So really amazing work by Dr. Wang. And you could see here that you have this particular movement. It was a very subtle movement where the finger moved along the z-axis. And what you could see here is that basically a lot of the movement is here. And in FMpre as well as in FMpost, you could see that it is identified. However, during the twitching, when the finger twitches along the y-axis, you see it still in the piezoelectric, and then you also see it in the three-dimensional MEMS. But then the process of filtering, the FMpre sees it, but the FMpost attenuates it significantly because this movement is not aligned along the gravity vector. And so I think there's some important differentiation. The piezoelectric accelerometer is sensitive along all the X, Y, and Z directions, whereas the FMpost is sensitive in the gravity direction. And FMpre is sensitive to all three directions. Another interesting thing is, there's some movements such as rotational movements. This is FMpost processing as the wrist is changing along its axis. And you can see that this appears here. However, in FMpre, so the FMpost sort of doesn't denote this rotation that well, but whereas FMpre, you see the rotation much better. So in summary, FMpre is sensitive to small motions, including rotational movement, whilst FMpost has a directional bias along gravity vectors. And so you could potentially use this to your advantage if you wanted to sort of delineate sort of the different types of activities that your study participants may experience. Now, this difference between FMpre and FMpost actually gets even more complicated when you're considering the activity count transformations. So let's just say, for instance, here, you are taking zero crossing modes to the FMpost data. And you can see sort of the FMpost data here in blue, the zero crossings marked as green crosses in the threshold. And you can see that the final zero crossing counts matches pretty well with the actual magnitude of the acceleration. However, if in FMpre, when you apply the zero crossing mode, you can see the magnitude increase here, but because these values don't cross this threshold value, your activity count or your zero crossing can actually falsely be low. So when you're applying the zero crossing mode with FMpre, it really is something that you should be cautious about. And when you're talking about energy level, they both work pretty well. But again, FMpre is, as mentioned before, more sensitive to smaller movements. So the values overall are greater for energy or PIM. And also the same for time above threshold. The FMpre is more sensitive to small movements. And this is an example of, actual data of a person walking at a particular pace. And you could see the FMpost in green and FMpre in orange. And again, as mentioned before, at least for FMpre, when it comes to zero crossing mode, you have a falsely reduced level. And so you could see this in this setting. In FMpre, during energy or proportional integration mode, FMpre is larger in FMpost. And the reason it's larger is probably because you have more horizontal movement. Now, remember, FMpost is more biased towards movements that's vertical or aligned with the gravity vector, or there may be a rotational movement. So you could sometimes see this difference and then differentiate the type of movement that you're dealing with here. And then you can see that FMpre saturates pretty much here. And so in summary, FMpre is sensitive to small motions, to rotational movements. It can be relatively incompatible with zero crossing mode and easily saturated with time above threshold. FMpost has some directional bias along the gravity vector. And so there's some metric compatibility here in terms of the type of acceleration signal that you get and the activity metrics. And this is something that we need to consider as you're doing your study.